12th lecture of the course on polymer chemistry, and in this lecture I plan to continue the discussion on chain transfer reaction and their implications, and then we talk about the inhibition and retardation reactions. We talk about how to determine or what is the procedure of determination of different reaction rates, rate of initiation, rate of termination, rate of polymerization, and we talk about and discuss how to determine the rate constant, different rate constant, and we will discuss about their magnitudes, and we go next to the auto acceleration gel effect, and then finally we will talk about the effect of temperature on polymerization rate and as well as effect of temperature on molecular weight of polymer. In last lecture we introduced different types of chain reactions possible, and we also convince ourselves that if there is a chain transfer reaction, except if the chain transfer is by the reaction with a polymer chain, dead polymer chain, in all other cases if the chain transfer happens, then molecular weight comes down. And we also introduce the term kinetic chain length and how it related to the average number average degrees of polymerization, and how we can determine initiator residues per chain and how that is related to the number of degrees of polymerization. Okay. Now, let us continue the discussion we were having in the last lecture on the chain transfer reaction. Now, we had discussed these molecules and their reactivity. Now, as we are discussing that if the most stable radical will have a tendency to react or undergo transfer reaction compared to the less stable one. Now, let us look at the values of these solvents. Cs is the chain transfer constant for the solvent. So, the higher the value, the higher is the tendency for that solvent to undergo transfer reaction. Now, we have listed here the values for two monomers, polymerization of two monomers, polymerization of styrene and polymerization of vinyl acetate, and look at the value. You will know that this is the most stable radical, then this secondary radical, then this one, then this, and in this case because again this is a primary radical. So, this stability would be similar to stability of this radical. So, look at the number again: benzene, cyclohexane, toluene. If you increase it will go toluene to ethyl benzene, isopropyl benzene, the tendency of transfer reaction goes up, and again we go to tertiary butyl benzene, because again it is a primary radical we are talking about, the tendency of transfer reaction goes down. Now, this happens to vinyl acetate as well, okay. But look at the comparison between vinyl acetate styrene. Vinyl acetates are, the numbers for vinyl acetate are higher. So, the tendency of these solvents for transfer reaction for vinyl acetate is higher compared to a polymer reaction of styrene. Now, what could be the reason between the difference in this tendency of this solvent towards different monomers? Again, as we discussed in the last lecture, if this propagating radical is very reactive, then obviously it will react for both the monomer as well as the solvent in this case. If it is less reactive, then it will choose the most feasible route. Now, between styrene radical propagating radical from a styrene polymerization and vinyl acetate polymerization, this is much more reactive compared to a styrene radical generated from styrene molecule. So, this will react much more 2 with the solvent molecule in this case. So, that is the reason this is this transfer constants has much higher value compared to styrene. So, if we want to list or rank between different monomers, the rank of the reactivity would be something like this. It is vinyl chloride higher than vinyl acetate, acrylonitrile, methyl acrylate, methyl methacrylate, styrene, and so on. So, you can yourself from your knowledge from organic chemistry, you can justify this ranking, because this is the most reactive. The radical generated from vinyl chloride will be much reactive compared to the other ones, okay, because this lacks any significant stabilization mechanism either by resonance or by inductive effect, okay, whereas styrene will have stabilization, radical generated from styrene will have the stabilization by resonance. So, the reactivity of that radical will come down. Now, this ranking does not hold always. There are cases where there is a specific interaction or affinity between monomer molecule plus solvent. Okay. There is specific affinity between this. If, for example, if the monomer is electron donor, it will have more tendency to react with a solvent which is electron acceptor, whereas if the monomer is a electron acceptor, it will have a tendency to react with a electron donating solvent. For example, let us compare between two monomers and two solvent and see whether we can justify or we can have this verified from the experimental data. Now, I considered triethylamine as a solvent. Now, it is electron rich. So, electron donor, and CCl4 which is electron acceptor. Solvent. Now, I compare between acrylonitrile and vinyl acetate. Now, acrylonitrile is a electron accepting monomer, where this is electron donor. So, obviously, this will have more tendency for react or undergoing transfer reaction with CCl4 than trimethylamine, and between these two monomers, acrylonitrile have more tendency to undergoing transfer reaction with triethylamine compared to vinyl acetate. So, if you compare the values, and put a third monomer methyl methacrylate, which is again a electron accepting monomer, and let us see whether it is more generic. So, acrylonitrile will prefer reacting with this as a transfer reaction compared to this, whereas vinyl acetate will reacting more with this than this. So, compare vinyl acetate, it has more tendency to transfer reaction with CCl4, with an acrylonitrile has more tendency to undergo reaction with trimethylamine. Now, between when comes a competition for same solvent, two monomers, because this is donor, it will have more reacting transfer reaction tendency with acrylonitrile. So, if you look triethylamine, the value is higher for acrylonitrile than vinyl acetate. Okay. So, you can justify the values for methyl methacrylate, which is again a electron accepting monomer. So, in what is the utility of transfer reaction, or what is what it can help you in this learning on transfer reaction? If say if you are trying to polymerize a monomer and then at the end you are not able to get the high enough molecular weight which you planned from your experiment, then what are the possibilities it could happen? If it does not build molecular weight, that means, and you know that from the monomer structure that it is polymerizable by say radical polymerization route, then there could be transfer reactions happening. It could be happening with monomer, initiator or solvent, or there could be impurities present in the reaction medium. Now, if you can remove, you can do the reaction once again removing all the impurities, and still if you can get or you do not get the high enough molecular weight, then what you need to look for is the structure for the initiator and the monomers and the solvent, whether they can take part in the transfer reactions, and you have to rule out the possibilities. If you rule out all the possibilities of transfer reaction by appropriate choosing the initiator and the solvent, then you can build the molecular weight. If it is the transfer reaction is because of the monomer, then there is no other alternative, you have to choose a different monomer altogether. If there is a transfer reaction is happening with the monomer, then there is no other way you can build the polymer molecular weight, because you have to use the monomer to make the polymer. Now, if you found in your reactions there is a very high molecular weight which you do not want, then what you can do, you can use these chain transfer agents which have. Now, what would be the good chain transfer agents which can easily participate in chain transfer reactions, and those molecules like SS and thiol containing SS and thiol. For example, if I look the values for 1-butane thiol, this number is very high, because in this case this is a very weak bond. Okay, so, easily this hydrogen can be very easily abstract by the propagating radical. So, by using this type of chain transfer thiols or dithiol compounds, you can reduce or control your molecular weight much to of your choice or if your target. Now, if you look at these solvents, carbon tetrachloride and carbon tetrabromide, they also have very high chain transfer constant. That means, these solvents are very poor solvents if you want to build high molecular weight in radical polymerization. The reason for these monomers or the solvents to participate in chain transfer reaction is because of their stabilization of the resulting ions. So, if I have, for example, I talk about on participating transfer reaction, it produced this radical. Now, this can be easily stabilized by all these bromine molecular which can participate in the resonance structure. So, that is the reason that this type of solvent, carbon tetrachloride and especially carbon tetrabromide, participate in the chain transfer reaction in very much high extent. So, always avoid this type of solvent or any halogenated solvent in that sense, because halogenated solvent will always be easily can be easily abstractable. Always try to avoid this halogenated solvent, especially for this carbon tetrafluoride and carbon tetrachloride type solvents. Now, if I look at that transfer reaction one more time, see if I take a new, so Y B into X A, I am writing Y B, and now it is producing M N Y plus B dot. K Z is the rate constant for reaction. Now, if this B dot, which is this radical, it is very stable, that it does not take part in further reaction, further chain initiation reaction. It might degrade or it might react with itself, forming non-radical species, but it does not react with a monomer to initiate the chain molecules, new chain, or if it is at all reacting with the monomer, the rate is very small, okay, which means practically in this reaction, transfer reaction, you are producing a dead chain. Okay. Even if you are producing an radical which is as good as a dead chain, because it is not taking part in initiation of a new chain. In this case, what happened? If K Z is much higher than K P, which means that this reaction is happening at much higher extent compared to the normal propagation reaction, then you will not have a polymer at all, because as soon as this chain initiates, it will react with this and form a dead chain. Okay. So, you will not have at all any polymer. So, polymer is get inhibited. So, it is a inhibition reaction, and this Y B is a inhibitor. If K Z is little higher or maybe comparable with K P, then what happen, part of the M N is undergoing this reaction and part of the M N is undergoing normal propagation reaction. So, what happen, your rate of polymerization become slower. So, this is a retardation and the molecule called retardants. Okay. For example, if I talk about a self initiated thermal polymerization of benzene styrene at 100 degrees centigrade. This is percentage of conversion and this is time. Okay. It is normally have reaction rate of reaction like this, with time more propagation happening. So, more monomer is undergoing polymerization reaction. So, higher is the conversion. If I add, this is 0% any external molecule. Okay. So, there is no external molecule in this case. If it is 0%, 0.1% benzoquinone, this is benzoquinone. Okay. So, what happened, for some time there is no polymerization reaction at all, the monomer is not consuming at all. Okay. Which means, as soon as radical is formed, it is reacting with your benzoquinone present. So, there is no polymer, no monomer is converting into polymer. Once this benzoquinone is over, then the polymerization reaction start normally. Okay. Now, this is a typical example how these common monomers are shipped or stored, because most monomers when they are shipped from between different countries or locally, they are stabilized with small amount of these inhibitors, for example, hydroquinone or benzoquinone, because they should not self polymerize either by little bit of heat or from the ambient or by self initiation reaction. So, when you do reaction, best way is to distill out that benzoquinone or hydroquinone stabilizer or inhibitor, or you can add little excess initiator compensating the inhibitor molecule, so that the don't reaction till all the benzoquinone or hydroquinone get consumed. After that, normal reaction happen. Now, there is a third possibility is like this: 0.5% nitrobenzene. In this case, reaction starts from beginning, okay, but with a much smaller rate. So, it is example of a retardation. There could be fourth possible, which is a combination of inhibition and retardation, something like this. Okay. It starts after some time, as well as the reaction is slower. This happens if we add 0.2% nitrosobenzene. So, these are the reaction possible, okay, with different types of this is a typical how it happen if you have inhibitor or a retardation or a combination of both of that. And the examples of inhibitors, again this is when these radicals is very stable. For example, if I have a butylated hydroxytoluene, now, when this forms a radical by abstraction of hydrogen, you can, I am not writing, you can imagine that the dot will come here, and which is basically extremely stable radical, which does not participate in the initiation reaction. It might degrade or react with itself, but it does not participate in. So, it is example of inhibitor. The other example is like 2,2-diphenyl picaryl hydrazine DPPH. When it react with this is extremely, it does not react with any monomer, it reacts with the only radicals and form a non radical species. This benzohydroquinone can react with a propagating radical and from either this or this radical, both of which are very stable radical. Okay. So, that is the reason they act as a inhibitor molecule. Another very common inhibitor which we come across always is oxygen. Okay. This can react to this self form non radical species, and this can form with another Mn dot and can form a non radical species. Okay. So, that is the reason that, and the transfer coefficient or the transfer constant is very high for this reaction. That means, tendency of oxygen molecule to undergo this reaction is very high, extremely high. So, which means that when you do reactions, chain polymerization reaction, radical chain polymerization, you must remove the oxygen molecule from the reaction medium as much as possible to avoid this killing of the radical, propagating radical, by which it will stop the reaction and also reduce the molecular weight. So, we have now learned transfer reaction and inhibition reaction and deterioration reaction as well. Now, let us talk about how one determine these different rates experimentally. By experiment. Okay. Now, Rp, which is the disappearance of the monomer or reaction of monomer from the reaction medium. You can directly determine the monomer concentration by taking alicot from the reaction medium and precipitating the polymer, and then weighing the polymer to find out the yield, which means rest is the monomer. So, by which you can know what is the monomer present or how much monomer is reacted. You can directly do it from a solution. So, direct alicot can be taken at different time frame and the polymer can be precipitated out from the reaction. Second, you can directly measure the concentration either by say spectroscopic technique or any chemical techniques. Now, it can be applied not only for radical polymerization, these experiments can be done for step polymerization as well, where you can stop the reaction in between and find out the functional group in case of step polymerization, but in case of this is the concentration of monomer molecule. So, from this you can get the value of Rp. Now, we get it once more time, this the expression for Kp is just for a reminder that this is this. So, we know this now from the experiment, and we can find out the concentration of M as well. So, this Kp and M dot are the two unknown quantities. Now, this M dot in theory or in principle can be found out directly from a ESR measurements, which can get the total initiator concentration, especially at the steady state, but because the lifetime or the lifetime of these radicals are very small, this normal ESR techniques is not very accurate to find out the concentration or M dot, the value of M dot. So, ESR is does not give a very accurate results of the M dot value. Now, we know Ri is minus di by dt. So, we can find out the I, initiator molecule concentration with time. So, we know the value of R I. So, we know value of R I, we also can find out the value of I. So, you know the value of AFKD. Okay. This is known now, this is known, this is known. So, you know this. Okay. This is for thermal polymerization. So, we can write the expression one more time for the rate of polymerization for thermal polymerization is Kd I by Kt to the power half. Now, in this expression we know this, we know this, we know this, we know this, we know this. Okay. So, these are all known. What is unknown is Kp by Kt by half. So, this is unknown quantity. Rest of the things we know from experiment. Okay. Now, how do we get this? To get this, we found the average lifetime. We define average lifetime of a radical at steady state. At steady state, tau s is the concentration of total radical species at steady state by the rate of termination square or by 2 Kt. So, now this can be, we can put this value of Rp here. So, we can get Kpm by twice Kt Rp at steady state. So, if you know tau s, we know Kp by Rp. So, from the value of tau s, we now know Kp by Kt. Okay. This is known, this is known. So, this by this has to be unknown, this is unknown. So, you know this. Okay. So, you know this, we know this. If we both are known, then obviously Kt is known, and if Kt is known, Kp is also known. Okay. So, this is the logic. Now, how do you determine this? There are two established methods. One is rotating sector method, and second is PLPACC, which is pulsed laser polymerization size exclusion chromatography. Pulsed laser polymerization size exclusion chromatography. Now, I am not going into detail about this method, how they are used to determine the value of tau s, but because this is not the scope of the course, but for your knowledge that these are the methods are applied to get the value of tau s. And now, once you know the value of tau s, you know this, and we know from this expression this. So, we know Kp Kt. So, now we know that by experimentally we can know the rates, the individual rates, we know Ri, we know Rp, we know Rt, and we also know Kd, Kp, Kt. We know all this from experiments. Now, what is the typical values of this? What are the typical values for radical polymerization? Ri is twice f Kd I, Kd is 10 to the power minus 6 to the power 4 second inverse. I typically used so RT comes around similarly RP m dot value typically is between 10 to the power minus 9 to 10 to the power minus 7 moles per liter. Kp is 10 to the power 2, 10 to the power 4 liter mole inverse second inverse. So, Rp value is at steady state, Rp value is minus 4 by minus 6 mole liter inverse second inverse, and Rt is twice Kt m dot square. M dot value is listed here. Kt is 10 to the power 6, 10 to the power 8 liter mole inverse second inverse. So, if you compare the values, typical value, these are the typical values. Now, the values could be different for different monomers and solvent choice, and also it could vary on it could vary on the various methods you have utilized to determine these values. Okay. So, it depends on the method, it depends on the monomer and the choice of solvent, but this is the typical values of the different rate constant and rates. Now, look at this number, Kd is very small, whereas Kp is much higher compared to Kd. So, the dissociation or the initiation reaction is very slow, Kp is fast. So, the propagation reaction is fast and termination reaction is much faster. Okay. But it does not mean that the rate of termination is faster, because the concentration of m dot is very low. Okay. The rate constant is very high, the reaction is intrinsically very fast, but because the concentration of the radical species is very low, the rate of termination also low, and that actually enables us to reach a steady state. Okay. So, again just for one more time, that the initiation rate constant is much lower compared to a propagation chain propagation, which is much faster reaction. Rate termination is much faster, even faster reaction, but at steady state the rate of initiation and rate of termination becomes equal, because the concentration of m dot is much lower. Okay. It is about 10 to the power minus 8 moles per liter. Now, what are the assumption if when we deduce this expression Rp is Kpm what are the assumptions we made? One was that initiation was slow, propagation was fast and termination was even faster. We had convinced ourselves now with the values of the individual rate constant that our assumption was not inaccurate, our assumptions was accurate. We also assumed that the individual rate constant for the propagation steps were equal. That means, the reactivity of a propagating radical towards a monomer does not depend on the length of the polymer chain at end of which the radical is present. Okay. And we have found that to be true as well. What we did not consider is that during polymer reaction we know that it is a exothermic reaction. Now, once the exothermic reaction happen, if we do not have arrangements to take out that heat which is evolved during the reaction, then there will be a change in temperature. If we cannot take out that heat which is generated by the exothermic reaction during the polymerization process quite effectively, then the temperature will rise, and once the temperature will rise, all these rate constant will also vary. So, the rate of polymerization is also vary if we cannot take out this the heat which is generated due to polymerase reaction, that we did not consider deducing at this steady state kinetics. Now, if I consider this, then how this rate will look like? So, let us plot RP versus conversion for a bulk polymerization, that means 100% polymerization. Again remember RP is Kp m dot. Now, initially before the steady state happened, m dot increases slowly before its steady state happened. So, with very low conversion it will take little time to steady states to happen. So, that is the transient non-steady state before the steady state happen. This is transient, it does not take much longer time, or does not take too much conversion to achieve that. Now, once the steady state have reached, RP will be almost constant, but with time what happened to concentration of M? Monomer concentration decreases. Steady state means the concentration of m dot is fixed with time. So, no change in the concentration of m dot. So, this is constant at steady state, but with more and more reaction happening, more and more conversion happening, m should go down, concentration of monomer should go down. So, RP would go down slowly. Okay. So, it go down slowly. Okay. Now, if at this moment if the medium viscosity is quite high, what happened? If the medium viscosity has become very high, so that the chains are not diffusing at the same rate when the viscosity was lower. Now, we know to termination to happen, termination is a bimolecular reaction between say two propagating radical. We know termination could be by either coupling or by disproportion reaction. Now, if these two cannot diffuse fast enough to find each other and react, then obviously the termination rate will come down, it will become diffusion control. That means, the intrinsic reaction is very fast, but the rate at which these two radical is finding each other is determine the diffusivity of these molecules. So, the termination reaction become diffusion control. Okay. The higher is the diffusion, higher is the termination reaction, but because medium viscosity is quite high, so diffusion rate is low. So, the termination reaction is low. Now, once the termination reaction is low, steady state is lost. So, more and more radicals are not terminated now, because rate of termination has come down. So, the concentration of m dot increases, okay, because the viscosity is very high, the reaction, the termination reaction has become diffusion control. It is difficult, that the propagating radical is finding difficult to find another propagating radicals to undergo a bimolecular termination reaction. So, the concentration of the propagating radical goes up. Now, once this concentration goes up, what happened to the rate? If this goes up, rate goes up, rate goes up. Now, we know del H is negative exothermic reaction. Once rate goes up, more and more heat evolved, okay, and more heat evolved means we will know in a minute that if we increase the temperature of the medium, rate of polymerization even goes up. Okay. So, what happens if there is a auto acceleration is happening, because rate goes up, rate of polymerization goes up, more heat is generated, we cannot take out effectively that because the viscosity medium is high. So, temperature goes up, as temperature goes up, rate of polymerization again goes up, as the rate of polymerization goes up, more and more heat is generated. So, basically there is a auto acceleration, the rates zooms, the rate of polymerization becomes too much accelerated, as a result you get a gel at the end. So, you get a gel, it is a very high viscous material. So, it is a gel effect, this is called gel effect, this is gel effect, or is called Tromsdorf Norris effect. And this is steady state. Now, for a bulk polymerization, this rate comes down drastically at the end. We will come and discuss why in a minute from now. Okay. So, this is in actual case, if the rate of polymerization depends on the conversion. Now, obviously, this gel effect, whether it will exist or if it exists at what conversion, that will depend upon the viscosity of the medium. If you are doing reaction in a solution, then if your concentration of the monomer in the solution is lower, then viscosity does not go up that much, and because the polymers are forming in the solution, the heat management is very good. So, there is no heat accumulation or no increase in temperature. So, the gel effect does not happen. So, if we plot a methyl methacrylate polymerization at 50 degrees centigrade in benzene by benzoyl peroxide initiator, it looks like this: time percentage conversion, okay, which basically gives the rate of the polymerization. Time versus conversion gives you rate of polymerization. When the 10% monomer in the solution, the reaction you are doing in dilute condition, the heat management is very good, viscosity is not high. So, no gel effect happened. Okay. If you do it in a little higher, say about 40%, you get like this. If it say 60%, this is 60% monomer in the solution, you get gel effect. 80% you get even before that. This is 100, okay, 100% conversion. This is bulk. Okay. So, this conversion versus time gives you rate of polymerization. If you do it at a 10% concentration, then the rate goes down slowly, but no gel effect happen. It does not happen for 40% as well, but if the concentration of the monomer is very high, 60%, then there is a gel effect. If it is even higher, the viscosity of the medium becomes very high even at low conversion at lower time. At 80%, it gel effect initiates at much lower conversion at lower time, and even bulk for which is 100% monomer, it happens even before that. Okay. So, you are now convinced, or you understand this, you understood this concept. Now, one thing you might have noticed that for 100% bulk, whether 80% or 60%, it has reached a 100% conversion of the monomer, but for a bulk polymerization, 100% of the monomers has not reacted and make polymers. Okay. It has not polymerized 100%. I mean, all the monomers present in the medium, they have not polymerized. Now, what could be the reason? Now, we know glass transition temperature. I have not discussed it in this till now, we will discuss in later, but time being, glass transition is the temperature at which a polymer becomes soft, okay, below which polymers become glassy. So, the mobility of the polymer chains becomes very low. Okay. So, below the glass transition temperature, the mobility of the polymer segments is very low and they have no translational motion, there is no translational movement of the polymer molecules. Now, if you do the reaction at the temperature which is below Tg, now Tg for polymethyl methacrylate is little excess than 100, is close to 100. So, if you do a reaction say at 50 degree centigrade or 60 degree centigrade, that is below the Tg, glass transition temperature. Now, Tg of a polymer also becomes lower in presence of solvents, in this case MMA as a monomer, okay, which is called plasticization, which is basically the reduction of Tg in presence of any solvent. In this case, solvent is the monomer itself. So, Tg drops down. Now, as long as your reaction temperature is above Tg of the polymer, in that condition the polymer chains have mobility. So, the kinetic chains have mobility. So, they can react with the monomer and participate in a polymerization reaction. The moment the reaction temperature becomes below of the Tg of the polymers in that medium, the polymers lose all the mobility. So, reaction stops, okay. The polymers becomes glassy. So, no reactions can happen, and this reduction of Tg from original 100 degree for polymethyl methacrylate will be lower. Reduction means the Tg value will be coming down more and more if you have more and more monomer in the medium. So, if you increase the conversion, that means more and more polymer forming, less and less monomer present in the medium, that means the Tg of the polymer present is becoming higher and higher, because you are reducing the amount of monomer present in the medium. So, if this is temperature and this is 100 degree centigrade is your Tg for PMMA in this case. This is mole fraction of the polymer. See, if this monomer mole fraction of the polymer is 1, then the Tg would be 100 degree centigrade for the pure polymer. Okay. If you have little amount of monomer, then Tg will come down, okay, plasticization will happen. More monomer, more plasticization. Okay. So, if you draw Tg with mole fraction, you are going to get like this. Okay. So, this is your glassy part. So, you have to carry out reaction a temperature below above glass transition temperature. Okay. And you know the glass transition temperature come down with more and more monomer present in the system or polymerization medium. So, in the bulk polymerization, as this is the point where the Tg has become lower, Tg of the polymer present in this case has become higher than the reaction temperature. If it is reaction temperature is 60 degree, in this case 50 degree. So, reaction temperature 50 degree, for Tg these polymers has become higher than 50 degree. So, no more conversion can happen. At this conversion, Tg of this polymer present, Tg of the polymethyl methacrylate present here had become higher than 50 degree, which is the reaction medium. Okay. So, once the polymer become glassy, then the polymer chain, the kinetic chain cannot participate for the reaction and cannot make new polymers. Okay. So, in the glassy region, the polymer cannot, in the glassy temperature is below the glass transition, it cannot make any more further, it cannot take up participate in further polymerization. So, what we going to do in the next lecture is we want to find out the effect of temperature in the polymerization rate and also the effect of temperature on the molecular weight of the resulting polymer, and we will talk about thermodynamics of radical chain polymerization in the next lecture.